Hello. Today we are moving to a new section. This is section 10.3. Um, section 10.3 is Isomorphism of Graphs. This is the chapter 10. Chapter 10 is Theory of Graphs and Trees. All right, section 10.3, Isomorphism of Graphs. The reason that we learn this section is let's say you are given a graph with a specific labeling of vertices and edges, and then you can just relabel the same graph in a different format and relabel the edges in a different format. Once you relabel them, you might think like you have two different graphs. All right, you might think like you have two different graphs, but they are not two different graphs. They are the same graph, but two different representations. All right, so isomorphism is helpful to recognize such kind of different representations. All right, let's say you are given a graph. Let's say graph A, you are given graph B. If these two are isomorphic, that means you don't have two graphs. You have only one graph. The problem is one graph is labeled in a different way than the other graph. All right, so that's the purpose of learning isomorphism of graphs. All right, let me to read these descriptions, and then I will explain every time when I need to explain that. All right, so let me read it. Two graphs that are the same except for the labeling. Okay, the graphs are same except for the labeling. Only the labeling is different. Vertices and edges. The labeling of vertices and edges are different, are called isomorphic. All right, are called isomorphic. This is a very important concept. You can check whether the given two graphs are different or the same graph. All right. The word isomorphism comes from Greek meaning same form. Isomorphic graphs are those that have essentially the same form. If graph is isomorphic to graph G prime, then we denote those graph as you denote this situation like this. You write G and then you put equal sign and then tilde and then G prime. Okay, this is equals, this goes like equal sign and at the top tilde. Those are called isomorphic graphs. All right, let me make a small change here. All right, so this is the definition. Let G and G prime be graph with vertex set VG prime and the edge set EG prime respectively. G is isomorphic to G prime if and only if there exists one-to-one correspondence. The correspondence is given here. That means there should be one-to-one correspondence between vertices and edges. Okay, so this is the one-to-one correspondence. Give me a second. This is the one-to-one correspondence between vertices. That's the one-to-one correspondence between edges. That preserves the edge endpoint functions of G and G prime, in the sense that for each V in G and E in EG, V is an endpoint of E implies GV is an endpoint of HE. I will explain everything later, okay? Don't worry. So first read the definition. You can understand the definition when we discuss an example. All right. So we have this example that we're going to discuss very soon. All right. So I will explain this part a little bit. Let's say this is the first graph you have, which is G. Okay. And then it has A, B, C, D. And then this is graph G. And then graph G prime is right here. Then it has vertices like this. P, Q, R, S. You can see these graphs are isomorphic. I'm sorry, when I want to say isomorphic, I pronounce it like homeomorphic, because homeomorphism is also a mathematical concept. In this class, we are learning only isomorphism. Homeomorphism is also a concept in math. So that's why I'm just confused homeomorphism and isomorphism. In this class, it is only isomorphism. All right. So you can see these two graphs are isomorphic. Why they are isomorphic? Because it's the same graph. Only thing happened is you just rotated one graph 90 degrees. All right. So then you can get the other graph. All right. So these graphs are isomorphic. Then let's say this is an let me mark this as let me mark only one vertex, because that's convenient. So let's say this is V and that is E. That means V is an endpoint of E. Then there's a function G that I'm going to explain later. That function will map vertices in this graph with vertices in the other graph, edges in this graph with the edges in the other graph. Okay, so these are two functions. Let's say the function is G, and then let's say this function, since this is V, that should map with this. All right, because this is just one point, this is just one point, and then this should map with that, this should map with this should map with that. That is how the isomorphism works. Okay, so let me use a different color for that. So this vertex should match with that vertex, and then this vertex should be matched with this vertex, and then this vertex should be matched with that vertex. That is how the mapping will work. And then finally this vertex should match with that vertex. Okay, so that's the mapping G that is explained in this definition. All right, now let's move to the example. In words, G is isomorphic to G prime if and only if the vertices and edges of G and G prime can be matched up by 1 to 1 onto function in such a way that the edges between the corresponding vertices correspond to each other. All right. So first of all, we have to understand what are one-to-one functions and onto functions. Okay. So what are one-to-one and onto functions? You learn this in discrete math 1. First of all, let's learn one-to-one functions. Let's say you have this set, which is x, and let's say you have that set, which is f of x, and then that is the function f. Let's say this has 4 elements. All right, so let's say this has four elements. Then what happened is the function works like this. Okay, that means for every single value here, there should be one value over here. Every single value here, there should be one value over there. If that happens, we call that is one-to-one. All right. If this happens, let's say this happen. Give me a second. Let's say this happens. Let me take that out, and that happens. That means this point is mapped by 2 points over there. So this is not one-to-one. Okay, this is not one-to-one. So let me mark those two cases. This is one-to-one. Let me mark another extra point. This is one-to-one. And the next case, I'm going to show a case where it is not one-to-one. All right, now let me see what will happen in this case. In this case, what happened is both of points are mapping into the same point. So this is not one-to-one. Okay, this is your knowledge from discrete math 2. Oh, sorry, 1. Discrete math 1. So then let me explain the case on 2. I use the same schematic for that. In onto case, what will happen is all the elements in this is called the range. All the elements in this set will be mapped by the elements in that set. Okay, all the elements in this set will be mapped by that set. Okay, so in this given example, you can see that this element is not mapped. Okay, so that's not onto. If this element is not mapped, so that is not onto. All right, so let me just take that out and let me think what I'm gonna do. Okay, I'm gonna make a small modification. I'm gonna take that out too. Wait, let me do something. I take that out. And See, this is onto, because all the elements in this set is mapped by elements in that set. This is onto. Now I'm going to show you a case where which is not onto. All right. In this case, what happens is there are elements in the right hand side set which are not mapped by the left hand side set. So how do I make it? So what I'm gonna do is I'm gonna add an extra point. Now it has 4 points. This is mapped to that. That is mapped to this. Alright, so this element is not mapped. So that is not onto. Now you can understand one-to-one and onto. Alright. Good. If it happens to be one-to-one and onto both, then this condition should be satisfied and that condition should be satisfied, one-to-one and onto. Alright, in one-to-one and onto case, all the elements in this set will be mapped only one element of that set, or each element in this set will be mapped by one element of that set. That is called one-to-one and onto. Alright, good. So then one-to-one onto. Let me make another graph quickly. I'm going to explain one-to-one and onto case. Alright, so if I delete that point, then this is one-to-one and onto. In one-to-one and onto mapping, every element in the right hand side set will be mapped by only one element from the left hand set. Alright, so now you understand one-to-one and onto. Let me get this more space. Good. Alright, good. Then go to the next slide. I'm still explaining the same slide. So let me get the lower boundary out. Okay, so you know about one-to-one and onto. Let me read this same paragraph. In words, G is isomorphic to G prime if and only if the vertices and edges of G and G prime can be matched by one-to-one and onto function, like F. Okay, like this F. One-to-one and onto. All right. In such a way that the edge edges between corresponding vertices correspond to each other. That means let's say this vertex, and just introduce another vertex. And just introduce another vertex maybe here, which is u. Oh no, let me mark it there, u. Alright, then if that is u, then this u will be mapped with that gu, because this function is g. And then here here this edge is e, that is between u and v. So this edge may be v prime, should map with this. Alright, so what I'm saying is this should be mapped with that. Alright, why they should be mapped? Because u mapped with gu, v mapped with gv, e should map with e prime. That is the edge between vertices. If two vertices are matching, then the edge between those two vertices should also match, which is explained here, in such a way that edge between corresponding vertices correspond to each other. Okay, that's what I explain here. So let me get that. Let me get that diagram below so you can understand. Copy. Then I will drop it maybe somewhere here. I will take this new mapping out, because that is not relevant to that graph. Oh, sorry, it should be there. By the way, last time I forgot to put HV here, HE. Alright, so go back here, and this is relevant to that explanation. This is relevant to the explanation of this part. Alright, so they are matching. Alright. Good. So let's move to the example. You can understand everything by the example. Show that the following two graphs are isomorphic. Right? You are given two graphs, you have to show them isomorphic. Isomorphism is something like you are checking whether one graph is a rearrange of labels of the other graph. Okay, these are having labels, these are the labels. So if you rearrange the labels of one graph, you have to make sure that you can get the other graph. If that happens, they are isomorphic. There's a way of checking that actually. Alright, so you see this small part here, so you can just bend that part over there. Alright, so you can just bend that part over there, then this is what you get. Okay, this is what you get, then that's not there. And you can that, and you can see these are same, right? Here this has that thing, this has that thing, and this has that triangle, this has this triangle, and then you see this is an edge which is same to that edge. Though this edge is bent, it goes like, you can just rearrange the edge like that, like a straight line. So this edge also goes like that. Now you can see this, they are same, right? They look same if you do that small rearrangement. But you have to show this mathematically. By my bare eye, I can see that they are isomorphic. My bare eye, I can see they are isomorphic. All right. Now I have to show that they are isomorphic mathematically. Okay. So I have just typed the solution. Now I'm going step by step explaining this explanation. I'm going to explain materials step by step. To solve this problem, you must find a function g goes from Vg to Vg prime. Alright, so this is the function you have to find. Alright, I will tell how to find that function later. That is the mapping for vertices. That is for vertices. And then you have to do the same thing for edges. That is the function for edges. Edge here, that is the function for edges. Alright, such that for each V in Vg and E in Eg, V is an endpoint of E, if and only if Vg is an endpoint of He, which I have explained already. See right here, which I already explained right here. So this figure is associated with that explanation. Alright, so let me get that figure over there. Let me copy this. Okay, that is explained right here. And then let's try to find that mapping. For instance, since E2 and E3 are parallel, you can see they are parallel. This is E2 and that is E3. Since E2 and E3 are parallel, HE2 and HE3 must also be parallel. Alright, so since these are parallel, these two edges are parallel, then the mapping for these two edges in this graph should also parallel. So what are parallel in the right hand side graph? You can see these are parallel, right? So these edges are parallel. That means these edges will map with these edges. That's how the mapping will happen. Alright, so that's explained in this paragraph. Since E2 and E3 are parallel, HE2 and HE3 must be parallel also. So HE2 equals F1, HE3 equals F2. Alright, so let me find this mapping right here. So the graph G has these vertices. I'm going to write down them in a set. it has vertices v1, v2, v3, v4, v5. Those are in G, the graph G, and graph G prime you have W1, W2, W3, W4, and W5. Let me rewrite them. That is G prime. So these are the vertices, and then at the same way, in the same way, just make sets for edges. So this is the edge set in G. Let me put G. Edges are V1 up to E1 up to E7. E1, E2, E3, E4, E5, E6, E7. Alright, in G prime, the edges are F1 up to F6. F1, F2, F3, F4, F5, F6, F7. Alright, so I have the sets now. Now I'm gonna represent them. So I already found this E2 will map with F1. The mapping function is H, so this is H actually. I'm sorry, this is H. H is the map of edges, and give me a second. Yes, H is the map of edges. This says E2 will map with F1. So find E2, which is right here, which map with F1. Now what I'm doing here is I'm finding the map. E2 goes like that. E2 map with F1, and this explains E3 map with F2, like that. Okay, that is the mapping of the first pair of edges. That means this edge map with that edge. This edge will map with that edge. Okay, which is marked here already. Now go down. Alright, now go down. The endpoints of E2 and E3 must correspond to the endpoints of F1 and F2. Alright, so that's the rule of the isomorphism. Endpoint of the edges should map the endpoint of the edges of the mapping. Okay, so let's see that. This is E2. Endpoint of E2 are V3, V4, and then since this maps with that, the endpoint also map. That means this should map with this. This should map with that. Okay. At the same time, this maps with this. Then endpoint also should map. That means this again. This will map with that. This will map with that. So the endpoint should map now. All right. So it's the same argument. If the edges match, then the endpoint of the edges should also match. All right, now I'm showing that in different colors. That is that and that are the endpoint of E2, and this and that are the endpoint of F1. Then they should match too. All right. The endpoints of E2 and E2 and E3 must correspond to the endpoint of F1 and F2. And so GV3 equals W1, V3 equals W1. That maps goes like that. This is the mapping G. And then GV4 should match with W5. V4 W5. V4 W5. Okay, they match like this too. All right. And then go down. Since the edge E1 incident to vertex V3, find whereas E1, which is right here, is incident to give me a second. Since E1 incident to V3, that is V3, the edge E1 corresponds to F3. All right, so we are matching like now. We have already matched this part. We have already matched that part with this part, and then you can now think of matching this edge with that edge and this edge with that edge. You are starting from one corner and then keep on proceeding. All right. All right. Now let me mark that information in this mapping. Now every time I'm bringing this map down because I can just mark on the same map. All right. Now what I'm going to do, I'm going to map E1 maps with F3, E1 maps with F3, and then E4 maps with F7, E4, F7. All right. Now I'm done with entire this part. All right, let me make a small change here. So now what I'm doing is I'm just making sure that I use yellow to mark the already mapped parts of the parts of the graphs. So let me get these out. I already mapped that, already mapped that, already mapped this, already mapped that. All right, without the vertex. Now what we have to do, think about the vertex. Vertex V1. V1 is the endpoint of 4 distinct edges. See, V1 is the endpoint of 4 distinct edges. In the other graph, W2 is the endpoint of 4 distinct edges. All right. So then this one should map with that. All right. Since V1 is the endpoint of 4 distinct edges, GV1 must also be the endpoint of 4 distinct edges. All right, so then we have to match them. All right, then go down. But the only vertex in G prime that has four edges coming out is W2, right? So that means in G prime it is W2, so they are matching. So then the matching function is this, that is the corresponding function. GV1 equals W2. This goes there. All right. And then let me get this even down. By counting in this way, possibly making some arbitrary choices as you go, you eventually can find function g and h to define the isomorphism between g and g prime. All right. So already you match this part and that part with this part and that part. All right, then you have triangular part. Triangular part is easy actually. You can say this should match with that. All right, and this should match with this. Once you do that, corresponding edges also match. That means this should match with this, and this should match with that, and this should match with this. Okay, that is how the isomorphism works. Now you have to fill the rest. V2 map with W3. All right, and then V5 match with W4. And in edges, E7 will map with F4, E7, F4. And then E5 match with F6. And then E6 should match with E5, F5. All right, so these are the mappings that you have already computed. Now you have to check whether they are one-to-one and onto. You have to check whether they are one-to-one and onto. In this mapping, they are one-to-one and onto. Why one-to-one and onto? Each element of G prime is only mapped by one element from G. So that is one-to-one. And here also the same thing happen. Each edge in this group will be matched by only one in that group. And the other thing is, to become onto, you have to make sure everything here is mapped. Yes, everything here is mapped and everything there is mapped. Okay, so they are one-to-one and onto. So we have to mark them. That's very important. Both functions are G and H are 1, 2, 1 and onto. All right, and go down. You have the same mapping right here as the solution. All right, let me delete this and let me make a small change. Since these are I'm talking vertices here, I replace the labels little bit. So I put V of G because they are labels, and here I put V of G prime, here E of G, there E of G prime, E of G prime. because we use E for edges and V for vertices. Let me take this function a little bit up. Alright, so that is the end of that example, and we are moving to discuss further details about isomorphism. There's a definition. Let me read the definition. A property P is called invariant for graph isomorphism if and only if, given any graph G and G prime, if G has property P and G prime is isomorphic to G and G prime has property P. Alright, so this is a very important definition. What this says is there are two graphs. You have G and G prime. Okay, there's property P, any property, that is number of edges, number of vertices, the degree, node degree, or maybe connected number of connected components, or anything. This property can be anything. All right. A property P is called invariant for graph isomorphism if and only if, given any graph G and G prime, if G has property P, let's say if G has property P, all right, and G prime are isomorphic, that means G prime has property P. Okay, so this is the result. This is the result here. All right, go down. Now theorem 10.2.3. Each of the following properties is invariant for graph isomorphism, where n, m and k are all non-negative integers. All right, the first property is n vertices. Let's say graph G has n vertices and then graph G prime has m vertices. If they are the graphs are isomorphic, then number of vertices should be equal. Okay, then edges. Let's say G has m edges and then G prime has n edges. If the graphs are isomorphism, the property will be equal. Or that means the number of vertices are invariant for graph homomorphism. And then edges are also invariant for graph isomorphism, and vertex degree is invariant for graph isomorphism. Okay, and then if m vertices of degree k of graph G, and then that also happen in graph G prime. If graph G has circuit of length k, then that also happen in graph G prime. All right, so there are 9 properties. If both graphs are isomorphic, these properties are common for both graphs. All right, so the sixth one is simple circuit of length k, simple circuit of m simple circuit of length k, connectedness. That means if the graph G is connected, graph G prime is also connected because they are isomorphic. And then Euler circuit. If graph G has Euler circuit, graph G prime should also have Euler circuits. All right, so keep that in mind. This is very important. This theorem is very important. And now we have an example. in this example, show that the following pairs of graphs are not isomorphic by finding an isomorphic invariant that they do not share. So you have to find any kind of isomorphic invariant, and then you have to show that that is not common to both graphs. It can be anything, maybe number of vertices. Okay, they should have the same number of vertices, and number of edges, they should have the same number of edges, or something else. Okay, let me check. You have this graph and that graph. The first easiest thing to do is count how many number of vertices in these graphs. Okay, so I'm counting vertices: 1, 2, 3, 4, 5, 6. Here 1, 2, 3, 4, 5, 6. Vertices, number of vertices are same. All right, so then that doesn't work. Now just count number of edges. With that will work. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Oh yeah, I counted wrong. Okay, I counted wrong. I counted this one. It is this is counted wrong. Let me recount this. 1, 2, 3, 4, 5, 6, 7, 8, and then this is 9. Okay, there are 9 edges, so they are not equal. Okay, let me put a note. Part A, the solution for part A. G has 9 edges. Whereas G prime has 8 edges. Alright, that's the solution for part A. And then go to part B. Again do the same thing. You have to show one invariant is not common. That's enough to show they are not isomorphic. Here first I'm counting number of vertices: 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It doesn't work. And then count edges: 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Oh, this in this time vertices and edges both are equal. Okay, now we have to try something else. Now count how many the degree. See, it says see degrees has a vertex of degree k. That means both having the same. Let's say if the first graph has vertex of degree k, then the second graph should also have a vertex of degree k. Okay, now I'm counting degrees. All right. Let me use a different color here. What is the degree? Degree of this one is 2, because there are 2 edges incident to that vertex. The degree is 2. What is the degree here? There are 1, 2, 3, 4 edges adjacent to that. The degree here, which is 3. Degree here, which is 3 again. All right. And degree here 2. Alright, then just count the degrees in the other graph. Degree here is 3, degree here is 2, degree here is 3, degree here is 3, and then degree here is 3. Right, now just check whether they have different degrees. There's one with degree 2, one with degree 2, and one with degree 3, one with degree 3, another one with degree 3, another one with degree 3, one with degree 2, no degree 2s here, right? One with degree 2, no degree 2s here, one with degree 4, no degree 4 there. So that is a good point. Or you can try that. H has a vertex of degree 4, whereas H prime doesn't have a vertex of degree 4. Okay, then they are not isomorphic. Okay, this tells not isomorphic. This tells not isomorphic. Alright, so that's the end of example, and then we are going to discuss about simple graphs. Alright, simple graph is a special type of graph, and this is the definition of simple graphs. A simple graph is a graph that does not have any loops or parallel edges. In a simple graph, an edge with endpoint V and W is denoted by V comma W because there are no loops or maybe parallel edges. Alright, so if you consider this graph, no loops and no parallel edges. Okay, no loops, no parallel edges. For this graph, that happens. No loop, no parallel edges. So that is a simple graph. It is clear to us. If you consider this graph, it has parallel edges or multiple edges. What are the multiple edges? This and that are multiple edges. This and that are multiple edges. Okay, they have multiple edges. Let me use a different color for that. These are multiple edges and those are multiple edges. In the next graph, there are some loops. First loop, the second loop. Alright, so only the first graph is a simple graph, other two are not. Alright, now we're going to discuss about a graph isomorphism of simple graphs. When graphs G and G prime are both simple, the definition of G being isomorphic to G prime can be written without referring to the correspondence between edges of G. Okay, so you can ignore the correspondence of edges. The reason for that is this doesn't have parallel edges or loops. Okay, the reason is simple graphs don't have parallel edges or vertices or loops. Because of that reason, you can just ignore the correspondence between edges. This is the definition. If G and G prime are simple graphs, then G is isomorphic to G prime if and only if there exists one-to-one correspondence. G from the vertex set VG to the vertex set VG prime. Alright. That preserves the endpoint function of G and G prime in the sense that for all V, U and V in G, U comma V is an edge of G implies GU comma GV is an edge in G prime. So this is what this explains. Let's say you have this graph. Okay, let's say this is U, that is V. So if this is an edge which is given by U comma V, this is U comma V. Okay, let me take this little away. How do I do it? Let me take this little bit down and then write that this edge is U comma V. Here we don't need labels for edges. Why? Because we can use labels of vertices because there are no multiple edges or loops. Alright, keep that in mind. Because of that reason, we only use vertex labels to denote edges. So this is GU, that is GV. So this is how the map works. And this maps with that. And then this is the corresponding edge. Which can be given by GU comma GV. Okay, so that is given right here. It is given right here. Alright, so go to the next example. Are the two graphs shown below isomorphic? If so, define an isomorphism. Okay, so you have to check whether they are isomorphic or not. Okay, for that you have to find out that the function of isomorphism. Okay, first of all, let me create the sets. Here it is A, B, C, D, and then X, Y, C, W. Alright, and then you have to find the map now. You can see this B is having only one edge connected to that. W is having only one edge connected to that. So B matches with W. Okay, then thereafter the corresponding edge goes like that, and then you could check this A, which has three edges incident to that. This Y has three edges incident to that, so A goes with Y. All right. Okay, actually WXYC. Okay, so I let me rearrange this because it should go like sorry, this should go like WXYC, right? So I just put in a wrong order. Let me go down. What I want to do is just take them out and write WXYC. Otherwise it will be confusing. So what I said was A goes with W, sorry, B goes with W, and then A goes with Y, and thereafter CD. This C is adjacent to A and the degree of C is 2. Then you can map C with X. And D with C. Okay, so this is the map. Now you can see this is 1 to 1 and on to. 1, 2, 1 and on to. That means isomorphic. Okay, they are isomorphic. So I just have the same function here. Let me mark this as VG prime, and then this function is, let's say it is G. Alright, so I have the function right here. The answer is yes. We have already found here they are isomorphic. Then we define this function G like that, and then this is the corresponding mapping, which is 1 to 1 and on to. Alright, then go to the next slide. Now we have to find the what do you call, give me a second, that is edge endpoint function. This is called the edge endpoint function. That means you have to find endpoints of each edge. This is graph G. This is graph G prime. And here it says the edge A to B. Edge A to B will be mapped with that WY. Okay, this W is same as GB. This X is same as GC. This Y is same as GA. And this C is same as GD. Alright, this is WY can be written down as GB comma GA. See, GB comma GA. Okay, let me copy that one here. AB, which is the edge between these two, this and that, is same as edge between this and that. Alright, and then A is, sorry, let me use a different color. A, C, A and C. A is mapping to Y, C is mapping to X. Then that is the edge between these two, which is GA, GC. And then the edge between A and D, A and D is same as the edge between these two, GA, GD. Alright, and then finally the edge between C and D is same as the edge between this and that, which is GC and GD. Okay, blue color is so sharp, so let me get that out. Let me take that light blue. And CD, and then that. All right, so they are isomorphic, and then you found the edge endpoint function too. So that's end of the today's class. Let's start the next section from the next day. Thank you very much.